Hey students, I hope you guys are doing okay. It is time to continue our population ecology discussion. Now that you have been population ecologists for a week, now we are going to be population ecologists for 2 weeks, and we are going to delve into some more topics that population ecologists concern themselves with, different realms of the subject of population ecology. We already covered abundance and different ways of estimating a population or determining abundance, whether it's direct counts or estimates or presence absence indices of abundance and the challenges thereof. And now we're going to look into some other aspects of population ecology. So in addition to abundance, what a population ecologist is interested in knowing is where is this population actually located? Where you have the entire area geographically where that animal can be found, this whole area that you see that's in orange, we refer to that as the geographic range. And the example here I give of bog turtles, you could say that their geographic range in North America is from southern New England all the way down to northern Georgia. Now their distribution is where they are specifically found within their geographic range. So whereas the orange line covers their geographic range, specifically where they are documented here is in this red grid. That would be considered their distribution. Now, as far as spatial population ecology, while distribution is important, where they're found within their geographic range, we also have a bit more of a complex concept as far as populations are concerned. And what we're seeing, or I should say, we're seeing this more and more as we have much more habitat destruction and fragmentation. That is, habitat that is cut up or separated from one another, fragmented, as you would say, because of human building, human interference. And that is if you have a contiguous population and you fragment their habitat, you wind up with little habitat patches. And we wind up with, when you have these patches of habitat and you have individuals of a population from one patch going to another patch, you have migration occur. We refer to that entire complex as a meta-population, and these little habitat patches are referred to as subpopulations. And what we have, or I should say, the defining, the difference between distribution and the metapopulation subpopulation construct you see right here is that in distribution, it's where the individuals are found, pockets of populations, but you're not implying that there's migration from one patch to another. Whereas in a metapopulation with subpopulations, you do have that phenomenon occur. That is migration occurring from one patch to another. What we refer to from connecting, or I should say what we refer to like the corridors, the connections of, well, I just said it, okay. The pathways or the areas that connect these patches where the animals migrate is referred to as a wildlife corridor. Now, I'm using animals as an example, but plants have subpopulation and metapopulation phenomena occurring as well. Even though plants are stable, their seeds can actually disperse in a metapopulation and subpopulation type of construct. Now, there is your key, though. What we want ultimately, in conservation, since habitat loss is the #1 reason for loss of species, we want to preserve all habitat. But in a growing population of humans, with so much development going on, inevitably habitat destruction and fragmentation occurs. And where you have a push from a conservation effort, is making sure that these habitat patches stay connected to one another, because if these patches are cut off from one another, no migration can take place, no movement can take place. And so you wind up having a population that is isolated in a small area. That would be considered a sink population. And in that way, they may run out of food, or they may run out of otherwise habitat like nesting space in order to survive. And or you may have inbreeding occur, and you risk that population no longer being able to live there. And so our conservation efforts focus on maintaining or reestablishing corridors between habitat patches. And one habitat uh, 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 one thing that cuts off corridors or destroys the corridors that we're very familiar with are roads. These big interstates cut off one particular habitat to another where animals cannot cross from one patch to another. And it can be something as big as an interstate where an animal can't pass over, or it could be small as a country road that has a curb. We think of large animals not being able to cross an interstate, or when they do, unfortunately, how many of us have hit a deer on the road? Way too many of us. They wind up not making it. But a small road that has a curb, you have turtles that can't get from one side of the road to another. They can't physically get up a curb. So it's not just the big highways, but we're talking about whether they're fences or housing developments. We in turn not only destroy habitat, but then we don't we cut these habitat patches off from one another. And so it's not what we say like the sexiest of ecology endeavors, ecological conservation endeavors, and we talk about that in conservation ecology, but this is where we see most of the push nowadays. You see here, this is a corridor that was built, it's an underpass where you had elephants that unfortunately were starving because they couldn't, daily what they would do is they would go from the valley floor up into the mountains to feed and to get water. And they couldn't do that because a highway was built. And so they wound up building an underpass, and the elephants use it, and their populations have benefited from that particular corridor from one patch to another. This is an interstate, and this is an overpass where animals are able to cross from one area to another safely, and it has been shown that they do use these. Here is another type of overpass. Now I don't, I think it's on the next slide. I don't show the Christmas crab video for one of your learning activities. The link is, again, I believe the next slide. But you have the migration of these Christmas crabs on Christmas Island, millions of them, from the land to the sea in order to reproduce, and then back to the forest again. And thousands were getting killed on roads. And so they guide the Christmas crabs through like aluminum flashing along the roads up to this bridge. They also have underpasses for their Christmas crabs. This is an underpass for reptiles and amphibians, so they can pass, in small mammals. And again, they have kind of guides to steer them to these underpasses. This is an underpass for reptiles and amphibians and small mammals. These are railroad tracks, and just like a curb, turtles can't get over railroad tracks, and so that connects one corridor to another. Sometimes you do have signs where you're not able to, put a physical barrier. You just have signs warning, look, this is it's hard to see, it's a toad sign. You have frogs and toads crossing this particular road. And so it's just telling you maybe you want to take another route. It's actually telling you the road's slippery because of that, which is really kind of gross. And so maybe what can be done, not what is done here, but you can close a road. And we see this certain times of the year down in the Cape May area with diamondback terrapin nesting, where they're crossing roads very often. This is a toad a road that's closed to allow toads to cross back and forth so they don't get smooshed by cars. Now, what we see here is, the really high profile effort for panda conservation in China is the captive breeding and reintroduction program. That makes the news, and you see baby pandas and nurses holding them and releasing them onto a reserve. But what they have done, which doesn't make the news because it's not as adorable or cute, is where pandas' geographic range was this whole area of China. Since then, they have wound up in these little patches, these habitat patches, their distribution where the corridors no longer exist because of development. And so where they've put their conservation efforts is to reestablish these corridors from one patch to another. Again, not only for feeding, but for breeding purposes. So they're able to exchange fresh DNA so you don't have inbreeding occur, which reduces the fitness of those pandas. Now, in addition to spatial locations, not only talking about geographic range and distribution, this is a bit of a different format. Let me kind of correct this. Geographic range, distribution, metapopulation, subpopulations, and wildlife corridors. There are other types of movements as well, where as a population ecologist, you may want to find out, or you may want to know for other purposes, where they're located as far as from a migratory standpoint. You have some migrations that occur due to having to acquire food. Some occur for reproductive endeavors. Some to stay away from predators. You have migrations that occur over long distances, thousands of miles, whether they fly or swim or walk on land. You have, and and most of these are what we say horizontal migrations. You also have vertical migrations where you have animals that might go from like the top of a water column to the bottom of a water column, just a few meters throughout a 24-hour period to protect themselves from predators. And this is considered a type of migration. Great to know. Where is these are little, looks like some sort of a zooplankton here, and in a lake. If you were going to do a population study on this type of zooplankton, and you have it's what we call a plankton net that you trawl behind a canoe or some sort of a boat, you put it in at a certain depth, and let's just say you're looking for them to do a study, and you put your trawling plankton net right here at the surface, and you don't catch any, you may wrongly assume that they don't exist. And actually, it's just the wrong time of day. Your net's not deep enough. If you go nighttime trawling and you go a few meters down and you don't catch any, you might suspect, oh, there aren't any of this type of zooplankton here, when actually you just have miscued their migration pattern, that daily vertical migration pattern. The great migrations of Africa, and they're still in North America here as far as different types of mammals. Salmon migration, you have a timing aspect to some of these particular migrations, temporal ecology, and we talk about that in one of our activities. The migration of salmon to get to their nesting grounds where they lay their eggs. Very important because it's a great food source for the bear that are there. As just an aside, sometimes it can be very problematic when we see climates that are changing, and you may have migrations that have occurred for hundreds, thousands, tens of thousands of years from one area to another. And you might wind up having an incongruous event where because of temperature changes, you might have a migratory insect or bird migrate a few weeks earlier than normal. And we have noted this in the past 20 years that migrations are occurring earlier because of the warmer weather in different regions. And when they arrive at their migration, from one area to another, the flowers and the fruits that they normally eat when they get to that migratory site aren't blooming or aren't there, because plants tend to bloom, tend to flower, tend to grow, not really just solely based on temperature, but also due to photoperiod, how much sun shines, which doesn't change. That doesn't change when the climate changes. So you wind up having, your population show up to this ground that they've historically migrated to for tens of thousands of years, and there's nothing for them to eat. We're seeing this more and more with birds. It's a big problem. And that is being examined, and what can we do about that? That's a big question in ecology at this point. It's very, very problematic, this incongruous type of migration. Now, there are other aspects that population ecology ecologists investigate. The whole you are assessing a population, you might be doing a mark recapture study, and you're recording, you're not just marking the animal, but you would also, for instance, be recording the age of the animal if it is known, whether it's a hatchling or a juvenile, or depends on the animal. Fledgling is a term that's used for birds. Whether it's of reproductive age or post-reproductive age, geriatric. Also, male versus female. That's another aspect of this that you would record, because, let's just say we are, as for ever and ever, in turtle populations, it's the girls that lay the eggs. So if you are only catching males, for instance, you might question, what is the future of this population if we don't have reproductive females? Or you might catch an equal amount of males and females, but all of your turtles that you're catching may be geriatric, or that might tell you that there is no recruitment into this particular population. If you're recording a healthy sample of males and females, and you have hatchlings and juveniles and adults and geriatrics, that gives you a window into how the future of the population, because there's lots of it tells you there's lots of recruitment going on, lots of offspring being born or hatched or what have you, and that they are surviving into old age. It's a healthy population. So it's something else that a population ecologist would want to know. Okay, how many are there? Of course, what's the abundance? But, the sex ratios and age ratios are also a reflection or a glimpse inside the health of that particular population. That's extremely insightful and important. Another aspect of population ecology is understanding your what we refer to as survivorship curves, population age structures. Some populations are, I should say, not some, but all populations have this, characteristic survivorship mode, and they can easily be graphed out, these type 1, type 2, and type 3, where you have, for instance, like type 3, survivorship curve is where you have a very high mortality in the first stages of life, but the ones that do survive to adulthood will live a very long time. Now, you see that here. So high mortality in the beginning, and then the few that do survive, the first, depends on the organism, the individual, or the species, the first few weeks or the first few years, will live to old age. That looks like some sort of a muscle that is there that many die at first and only a few survive to adulthood. Unfortunately, sea turtles are like this, and so knowing that, we can use some strategies for their conservation efforts. You know, it's said that only one sea turtle that hatches out of 10,000 makes it to adulthood. Those odds are really low. And so one conservation effort that I alluded to before in the species ecology lecture for sea turtles is the reason their mortality is so high is because when they hatch, if they hatch, because there's lots of predation that goes on the nest for the eggs, once they hatch and they make it to the ocean, they're so tiny. You know, some of them might only be the size of a $50 coin, and they just, it's like everything eats them. They're just such an easy meal for all the fish out there. And until they get to be like the size of not even a dinner plate, I'm going to say between a bread plate and a dinner plate, it takes a few years for them to get to that size, then they're not such an easy meal for so many other animals in the ocean. And so one of the strategies, because recognizing this is a type 3 species, the sea turtles are, population, all the populations of sea turtles are type 3, exhibit type 3 survivorship curve, is that there are conservation efforts where they monitor the nests, and once the turtles hatch, they take them to a facility, a guarded facility, and they hold them for a few years until they get to be between the size of a bread plate and a dinner plate, and then they release them into the ocean. Give them a bit of a leg up so they don't become, you know, the meal for everything there. Where you have a constant mortality rate, you know, it doesn't really make a difference on the age. The mortality rate is pretty much the same for the babies, for the juveniles, the adults, and the geriatrics. That's a type 2 survivorship curve, and you see that, you know, squirrels exhibit this. And then your type 1 survivorship curve is you do have a lot of offspring that survive and live a long time, and once a certain age is reached, then you have high death rate, and people fit into this category, this type 1 category. You know, the average age, I don't remember what it is in the United States nowadays. It's, I think, maybe 79 or 80 because it's come down the past few years. But you have a lot of people that live to that age, and then at that certain age, you wind up having a large die-off. That's important to know when you're forming strategies from the standpoint of conservation. Now, as a population ecologist, you would be interested in knowing how your population grows and what are the factors that regulate the growth of the population of your population, individuals of your population. Oof, boy, I'm having trouble with this one. In general, like two types of population growth. You have exponential growth, which is if you have no external factors and unlimited resources, habitat, food, water, that you will wind up having a population that grows exponentially, that doubles every year, and you wind up with what we would refer to as a J curve. Just keeps going up and up and up and up. Each generation you're doubling, and you wind up with this J curve. But in nature, what you hate to use absolutes, but I'm going to say 99.99% of the time, what you wind up having is what we would say an S curve. That is, there are resources in the environment that are not, I mean, almost all resources in the environment aren't unlimited. Food and water and habitat, shelter, etc. And so the amount of resources available will limit the number of individuals in that population in that geographic area. So whereas, you know, when you have plenty of resources available, the population rate goes up. But once you reach the point where there's only so many resources available for so many animals or plants, that population number, that abundance number levels out. You reach what is called carrying capacity. Wow, that's a huge word, and it's given so little credit just down here. The carrying capacity of a geographic area is how many individuals of a population can that geographic area hold, considering the resources that are available. We can only have so many gray squirrels on campus because there are only so many acorns available. And so what happens when you reach carrying capacity? You have the birth rate and the death rate are equal. And like if you have some sort of weird thing where, and I know they eat more than acorns, it's just to simplify the example, you for some reason lose a bunch of acorns, maybe your oak tree doesn't produce as many, you can't have as many squirrels on campus because there aren't as many acorns available, resources available. There's only so many nesting spots, there's only so much water. We can only have so many red-tailed hawks trolling campus because there's only so many squirrels available. And again, I know they eat more than squirrels, but to simplify the example, but your carrying capacity and what you'd say logistic growth, or your S curve, is how you have populations regulate, or how it is shown on a graph, how populations are regulated in any given geographic area. Now, you can have different factors that regulate populations, a number of individuals in any given population. There's density dependent and there's density independent. Now, density independent population regulating mechanisms, this is where it doesn't matter how many of individuals are in the population. These are events that will bring down the number of individuals regardless of how many there are. It's not, again, it's kind of reusing the phrase, but it's independent of those particular external factors. So like for instance, as you see there, like a forest fire, and if you have a forest fire, it doesn't matter if there are 10 squirrels in the forest or 100 squirrels. A fire is going to, the number of squirrels didn't cause the fire, and so therefore it is an independent factor. Any of these like natural disasters or weather events are considered density independent. Now, a student brought up, hey, what about, if you have some sort of invasive insect pest that eats your trees and dries them to kindling because there's so many dead trees, which causes a forest fire. Yeah, I mean, you can start making cases for that, but we're kind of muddling up the works here. And so we will just leave it at you have these density independent population regulating mechanisms. But then those mechanisms that are density dependent are generally the result of competition for resources. Again, there's only so many resources available. Intraspecific competition is where you have competition amongst the individuals of the same species for any given resource, and you see lots of different examples here of individuals that are competing over a resource, whether it's food or mates, or here's plants for space and nutrients in the soil. And it's the number of individuals which lead to the regulation of population. The density can affect, for instance, it's easier for disease to spread, for parasites to spread, which would reduce the population when you have more of them. When you have less individuals, this is less likely to happen. The number of offspring, we call that fecundity. When there tend to be more of them, there are more individuals, there's less resources. If you're not fed as well, you tend to produce fewer offspring. You have reduction in fitness. You do have adaptations that are result as far as density dependence as well, but from a population standpoint, these are like resources that are available or not that will regulate the number of individuals in your particular population. Now, you do have two types of interspecific competition which regulate the growth of a population that are density dependent. Exploitation competition, this is just where you have individuals that are competing for the same resource. They're using the same resource, but they're not fighting one another over it. They're not sparring. They're not coming in physical contact. They just happen to be eating the same thing. And there's a grasshopper and a bunch of grasshoppers in a small area. They are competing with one another for the food source, but they're not fighting with one another over it. That's exploitation competition. It doesn't make nature films. It's not real exciting, but it is a dependent competition mechanism. Dependent, density-dependent population regulating mechanism. I have trouble in live lectures putting all that together too. Now in nature films, you see individuals fighting with one another. Holy smokes. And they are sparring. It is quite dramatic. And what you have is when there is a resource that is limited, for instance, like food or space or mates, you have those individuals fighting one another over that particular resource. I don't think I have a learning activity that questions you about this. Here are some really cool links to some interference competition, which is where you do have these sparring duels take place. Two rams butting the heck out of each other. This one's just, I don't care for spiders, so I don't like watching that. It's wolf spiders fighting with one another. But the giraffe one, I highly recommend you watch that. It's very cool. It's just recently viewed in the wild or witnessed in the wild as far as two male giraffes who are vying for a hierarchy in their herd, really knocking the heck out of each other with their necks. It's pretty dramatic to see. So as much as it's not in one of our learning activities, I recommend you watch it. It's actually pretty cool. There's no blood or anything. It's just like a lot of like thumping of their necks going on. It's bizarre. So those are some other aspects to population ecology. As your second week here being population ecologist, I hope you enjoyed the lecture. The parrots were quiet, or the parrot was quiet. Ruby didn't scream this time. And I guess it's a time of day. All the dogs are snoring, so that's good. All right, if you have any questions, let me know, put it in the discussion, and I hope you're all having a great day. Thank you. Bye.